During the Cold War, Hungarian engineers conceived an unusual machine. Its initial purpose was the rapid decontamination of military tanks following a potential chemical, biological, radiological, or nuclear attack. The design combined the sturdy, tracked chassis of a T-55 tank with the immense power of two MiG-21 jet engines mounted atop the structure. Events, however, would steer this invention towards a different, equally dramatic role. Subsequently, this formidable creation became known as bigwind. Its function shifted from decontamination to combating catastrophic oil well fires. The concept was adapted for firefighting, generating an extraordinary force to extinguish blazes previously considered uncontrollable. Renowned firefighter Paul Neal Red Adair, famous for tackling hazardous oil well fires globally, was among the first to employ such technology. Operating the machine required a coordinated team of three. A driver navigated the tank chassis across difficult terrain. A controller, situated in a rear cabin, managed the powerful jet engines and the associated water jets. Overseeing the entire operation, a fire chief directed the efforts from a safe distance, typically about 15 feet away, using a remote control unit. When activated, 6 large water nozzles positioned above the jet engines would release a tremendous volume of water. This water mixed instantly with the superheated exhaust from the engines. The result was a high-velocity spray of steam and water, directed forcefully at the base of a fire. The water flow rate was immense, reaching approximately 220 gallons every second. To put that volume into perspective, it was roughly double the amount of water an average American household might use in an entire day. Connected to a typical suburban swimming pool, the machine could empty it in under a minute. In the year 1991, bigwind demonstrated its unique capabilities on a massive scale. Following the Gulf War, Iraqi forces retreating from Kuwait set hundreds of oil wells ablaze. Teams of specialized firefighters converged on the burning fields. Amidst the inferno, the powerful water-jetting machine proved invaluable in bringing some of the most challenging fires under control. A similar concept also emerged in Germany. A firefighting vehicle known as the Hurricane was developed, mounting a single R-13-300 jet engine, also from a MiG-21, onto the chassis of a T-55 tank. It operated by blowing a mist of water over fires from a distance. In parallel developments elsewhere, jet engine power found another terrestrial application, battling extreme winter conditions. When heavy snowfalls buried infrastructure, conventional plows sometimes proved insufficient. Engineers realized that the sheer force and heat generated by jet engines could be harnessed for snow and ice removal. The mechanics were relatively simple but effective. Jet engines produce thousands of pounds of thrust, a force capable of blasting away densely packed snow. Simultaneously, their exhaust gases reach extremely high temperatures, often around 1,000 degrees Fahrenheit. This intense heat could rapidly melt thick ice and stubborn snowdrifts. The combination turned jet engines into exceptionally powerful snow-clearing devices. During the late 1960s, New York City's transit authorities began using a jet-powered snow blower specifically designed for clearing railway lines. Its deployment significantly reduced the time needed to restore train service after major snowstorms. Work that previously took days using plows and manual labor could often be accomplished in a matter of hours. Around the same time, similar techniques were adopted in the Soviet Union and other Eastern European nations. Countries like Poland and Czechoslovakia began using truck-mounted jet engines to clear snow from vital airport runways and railway tracks. Czechoslovak railroad workers, for instance, employed a MiG-15 engine to defrost frozen tracks during a severe snowstorm in the 1970s. Despite their effectiveness, these jet-powered systems had drawbacks. Primarily their operational cost. The engines consumed vast quantities of fuel, making them an expensive solution. Consequently, many snow-clearing operations utilized retired aircraft engines, often sourced from decommissioned military jets. In the Soviet sphere, numerous snowblowers were fitted with Klimov VK-1 engines. The Klimov VK-1 was the first jet engine mass-produced in the Soviet Union, and had originally powered the famous MiG-15 fighter aircraft. While these engines might no longer meet the stringent reliability standards for flight, they were perfectly adequate for ground-based snow removal. An engine failure during snow clearing carried far less severe consequences than one occurring mid-flight. Even in more recent times, jet-powered snowblowers continue to be used in certain areas. Along the eastern seaboard of the United States, some railway lines still rely on these powerful machines during heavy winters. Much like their earlier Soviet counterparts, many employ repurposed aircraft engines, some dating back several decades to the Cold War era. Reports also indicate Russian forces have continued this practice, adapting old MiG-15 engines onto heavy trucks for clearing snow from airfields and even aircraft carrier decks. The sheer power generated by the twin MiG-21 engines on the bigwind was essential for tackling oil well fires. These blazes were notoriously difficult, fueled by immense pressure from deep underground. Conventional water streams often lacked the force to penetrate the core of such infernos. The jet-powered water spray, however, created a high-velocity blast capable of severing the fuel source from the flame. Its deployment in Kuwait after the Gulf War marked a significant moment in industrial firefighting history. The scale of the disaster, with hundreds of wells burning simultaneously, required extraordinary measures. The success of bigwind under those extreme conditions validated the unconventional approach. It demonstrated how aviation technology could be adapted for critical ground-level emergencies. Turning again to the challenge of winter, jet engines addressed problems beyond just deep snow accumulation. Ice formation on railway tracks and critically on switching points could paralyze rail networks. The intense heat from the jet exhaust proved highly effective at rapidly deicing these crucial components, ensuring trains could continue to operate safely. During the 1960s and 1970s, nations like Czechoslovakia and Poland regularly deployed MiG-15 engines for such tasks. The use of retired military hardware was a pragmatic solution. Developing dedicated, high-power snow-melting machines from scratch would have been prohibitively expensive. Utilizing engines like the Klimov VK-1 from decommissioned MiG-15 fighters, or the R-13-300 from MiG-21s for firefighting tanks, provided immense power at a fraction of the cost of new equipment. Reliability concerns that grounded these engines were less critical for terrestrial applications. These repurposed power plants represented ingenuity born of necessity. Whether battling explosive oil fires or uncompromising winter ice, engineers found ways to harness the fierce energy of jet propulsion long after its intended life in the skies had ended. The legacy of these machines persists. Reports indicate the continued use of truck-mounted jet engines for clearing airfields by Russian forces, employing the same principles developed decades earlier. The operation of these jet-powered machines, whether for fighting fires or clearing snow, was an assault on the senses. The deafening roar of the engines and the palpable force of the exhaust were testaments to their power. Logistically, maintaining these systems presented unique challenges. Sourcing fuel in the vast quantities required, especially in remote locations like the Kuwaiti oil fields or snowbound rail lines, was a significant undertaking. Furthermore, working with aging jet engines, even if deemed unsuitable for flight, demanded specialized mechanical knowledge for upkeep and repair on the ground. The Klimov VK-1 and Tumansky R-13 engines were products of a specific technological era. Adapting them for sustained, ground-level operation required considerable engineering skill. It was a far cry from the controlled environment of an aircraft hangar or a military airbase. The initial Hungarian concept, born from Cold War anxieties about CBRN warfare, ultimately found its most impactful applications in civilian and disaster response scenarios. The transition from potential weapon decontamination to battling industrial fires and natural phenomena is striking. It highlights a recurring theme in technological history. Innovations often find purposes far removed from their creators' original intentions. As events unfolded, the raw power designed for military supremacy was redirected to confront different kinds of destructive forces. These powerful hybrids, tank chassis fused with jet engines, stand as compelling examples of human ingenuity under pressure. They represent a unique intersection of military hardware, aerospace engineering, and practical problem-solving on a massive scale. The environments where these jet-powered machines operated were often extreme. Oil fields ablaze presented not only intense heat and toxic fumes, but also unstable ground and damaged infrastructure, requiring the robust mobility of a tank chassis. Similarly, clearing snow and ice from remote railway lines or expansive airfields during severe winter storms demanded solutions far more rapid and powerful than traditional plows could offer. Conventional methods struggled against the sheer volume or the stubborn adhesion of ice. In firefighting, particularly with high-pressure wellhead fires, the sheer force of the jet water stream was its critical advantage. It could push the flame away from the fuel source in a way standard fire hoses could not achieve, allowing crews to approach and cap the well. For snow removal, the combination of high-velocity air and intense heat offered speed. Keeping vital transport arteries open, whether railways in Czechoslovakia or airports in the Soviet Union, was paramount, justifying the high fuel consumption in critical situations. The skill required to operate these machines effectively was considerable. Drivers had to navigate treacherous terrain, while controllers precisely managed engine thrust and water flow, often in perilous proximity to the hazard. This reliance on repurposed military engines also reflects the economic realities and technological capabilities of the time. During the Cold War and its aftermath, vast inventories of such hardware existed, offering a readily available source of immense power. Developing entirely new machines specifically for these niche, extreme tasks would have involved substantial research, development, and manufacturing costs. Adapting existing, proven technology was a more pragmatic and expedient approach. Subsequently, while perhaps less common today due to improved conventional methods and the high operating costs, the history of these jet-powered ground vehicles remains a fascinating chapter in applied engineering. It underscores a willingness to employ brute force solutions when faced with overwhelming challenges.